created by Mindstick's Foundation Trust.
Hello, everyone, and welcome to today's Explainer. We've got an exciting session ahead. We'll quickly cover detecting small currents, move on to Faraday's electromagnetic induction, look at Fleming's right-hand rule, compare alternating and direct current, and finally bring it all together with the electric generator. Let's dive right in.
First up, Section 1, detecting small currents. Before we even start talking about lighting up entire cities, we really need to understand how to spot these smallest trickles of electricity. Take a look at this beautiful little instrument. It's called a galvanometer. Notice how the zero mark is dead center? It's not off to the side like your car's speedometer. This is crucial because when even a tiny current, we're talking just 1 milliampere, flows through it, the pointer deflects. And because it can swing either left or right from that center zero, it doesn't just tell us, hey, there's a current. It actually shows us exactly which direction that current is moving. Pretty neat, right?
All right, moving on to our second topic, Faraday's electromagnetic induction.
Normally, to get a current, we just hook up a battery, right? But what if we want to make that galvanometer needle jump without using any battery at all? Well, Michael Faraday figured this out with a truly groundbreaking experiment. Here, we just have a simple coil of copper wire hooked directly to our galvanometer. No battery in sight. But watch what happens when we simply push a bar magnet towards the wire. Boom! The pointer deflects. Pull the magnet away, and the pointer swings right back to the other side. Just the simple act of moving a magnet near a coil literally forces the electrical charges to move. That right there is Faraday's electromagnetic induction.
So let's pin down the formal definition. Faraday's law of induction states that whenever the number of magnetic lines of force passing through the coil changes, current is induced in the coil. Now, the absolute magic word here is changes. If you just hold the magnet perfectly still inside the coil, absolutely nothing happens. Zero current. It's that physical movement, the continuous changing of those invisible magnetic lines cutting across the wire that actually creates the electricity. Next up is Section 3, Fleming's right-hand rule.
Okay, so we've induced a current. Great. But how do we actually predict which way it's going to go? Well, we use a very handy truck, literally. Stretch out your right hand right now. Point your thumb, your index finger, and your middle finger so they're all at straight right angles to each other. Got it? Now think of it like this. The thumb stands for the motion of the conductor. The index finger points in the direction of the magnetic field. When you line those two up, your middle finger automatically points out the direction of your induced current. This brilliant little shortcut is known as Fleming's right-hand rule.
This brings us to Section 4, alternating and direct current. Now that we're generating electricity, we need to talk about the two different ways it can behave. First, we have direct current, or DC. This is the stuff you get from a standard household battery. It's stable, it doesn't oscillate, and it flows steadily in one single direction. On the flip side, we have alternating current, or AC. Just like the name implies, it alternates. It surges up to a maximum, drops back down to zero, and then completely reverses direction. It constantly changes its magnitude and its direction. Let's look at a visual representation to really make this click. See that blue line? That represents direct current. It's perfectly flat and horizontal, showing us that steady, continuous, one-way flow. Now compare that to the orange line showing alternating current. It's a sinusoidal wave, right? It rises up into the positive, dips all the way down across the zero line into the negative, and comes back up. That non-stop back-and-forth oscillation is the absolute signature of AC electricity. And here is a super practical fact for our daily lives. In India, the massive power stations generating our electricity produce it exclusively as AC. And they do it at a specific frequency, 50 hertz. To put that into perspective, it means the current changes its direction incredibly fast. One full cycle happens every 1/50th of a second. This exact standard is what continuously powers our fans, our fridges, and our schools. Finally, we arrive at Section 5, the electric generator. So, we've covered the textbook theories of Faraday and Fleming, but up until now, those little currents we talked about making with a galvanometer were, well, tiny. So I have a question for you. How do we actually take this principle of electromagnetic induction and harness it to produce the massive, usable currents needed for mankind? How do we scale up a simple magnet and wire to light up a bustling city? The answer, of course, is the electric generator. Let's break down its structure. Right in the center, we have a rectangular copper coil, which we'll call ABCD. It's sitting securely between the extremely strong north and south poles of a large magnet. The two ends of our copper coil are connected to these conducting rings, labeled R1 and R2. These rings are constantly rubbing against those stationary carbon brushes, marked B1 and B2.
This whole setup is the beating heart of large-scale power generation. Now, let's trace the mechanics step by step. First, some external machine, maybe a massive turbine driven by a dam's flowing water or pressurized steam, forcefully spins the central axle. Because that axle is turning, our copper coil starts rotating rapidly right inside that powerful magnetic field. And remember Faraday's law from earlier? Because the coil is physically rotating, it's constantly cutting and changing the magnetic lines passing through it. This continuous change induces an electric current in the branches of the coil. Finally, that fresh current travels down to the conducting rings, where those stationary carbon brushes pick it up and pass it out to the external circuit. And because the coil flips over every half turn, the current keeps reversing. That gives us an AC generator.
But wait, what if we specifically need direct current? What if we want the electricity to just flow in one straight direction without alternating? Well, it's actually a very clever engineering fix. To convert this into a DC generator, we just replace those two solid rings with a single split ring, very similar to what you'd find in a basic electric motor. Because of the split design, the side of the coil that happens to be moving upwards is always touching one specific brush, and the side moving downwards always touches the other. This little swap ensures that out in the external circuit, the current stops alternating entirely and flows in one steady, single direction.
We've covered quite a journey today, right? Going all the way from detecting a tiny, barely there flicker on a galvanometer to understanding the huge generators that quite literally power our modern world. We've seen how simple physical motion creates electricity. To wrap up this explainer, I want to leave you with a really provocative thought straight from your studies. Under the guidance of your teachers, how might the engineers of tomorrow use these very same principles of electromagnetic induction to attempt to build a free energy generator? It's a fascinating puzzle to think about as you continue your physics journey. Keep questioning, keep experimenting, and thank you so much for exploring with me today.